Tonight, we're about most impossible journey any to embark on the human has ever attempted. We're going to do something that would destroy the most advanced spacecraft ever built. Something that defies every law of physics we know. Something that exists only in the realm of pure imagination. We're going to fly through every single planet in our solar system. Not around them, not past them, but straight through their hearts. Through crushing atmospheres that would liquefy steel in seconds. Through cores so hot they make the surface of the sun look cool. Through magnetic fields powerful enough to strip electrons from atoms. Through storms that have raged for centuries and winds that scream faster than sound itself. This is a voyage no spacecraft will ever complete. No human will ever survive, and no technology could ever accomplish. But here, in this quiet moment, we can let our minds soar where rockets never could. We can experience the impossible, touch the untouchable, and witness phenomena that exist at the very limits of what matter can become. If you find comfort in these gentle explorations of the cosmos, I'd be grateful if you'd consider subscribing. The visuals are here for you, but feel free to close your eyes and let your imagination carry you through these alien worlds. There's absolutely no problem if sleep finds you somewhere between Venus and Jupiter. Comment your time and location below. It's always fascinating to see where we're all watching from across this pale blue dot we call home. Before we begin this cosmic odyssey, let me paint you a picture of what we're actually dealing with. Our solar system spans nearly 12 billion kilometers from the Sun to Neptune. That's a distance so vast that light itself, traveling at 300,000 kilometers per second, takes over 11 hours to make the journey. Within this enormous space, 8 worlds dance their eternal ballet around our star, each one a unique laboratory of physics pushed to extremes we can barely comprehend. We're going to visit them all, starting with the innermost world and working our way outward through increasingly alien environments. Some of these planets will greet us with temperatures that would vaporize diamonds. Others will try to crush us with pressures that exist nowhere else in the known universe. Still others will surround us with chemical cocktails so toxic they would dissolve our spacecraft before we could even begin our descent. But tonight, we're invincible travelers. We're immune to heat and cold, to crushing pressure and deadly radiation. We can breathe methane as easily as oxygen, swim through liquid hydrogen as comfortably as water, and witness the birth of lightning in atmospheres where no human eye has ever gazed. Our journey begins at the edge of possibility itself, with a world so close to the sun that its day side could melt copper, while its night side would freeze nitrogen solid. This is Mercury, the smallest planet in our solar system, a world of such extreme contrasts that it challenges everything we think we know about what it means to be a planet. As we approach Mercury from the darkness of space, the first thing that strikes you is how utterly alone this world appears. No moons grace its sky, no rings encircle its equator, just a scarred ancient sphere that looks like it's been through a cosmic war and barely survived to tell the tale. The surface is a patchwork of craters, each one a frozen moment from the violent early days of our solar system, when asteroids and comets rained down like celestial artillery. Mercury rotates so slowly that a single day here lasts almost 60 Earth days. Imagine sunrise taking 2 months to complete, the sun crawling across the sky at a pace that would make a snail seem swift. This sluggish rotation creates temperature extremes that boggle the mind. The day side reaches 430 degrees Celsius, hot enough to melt zinc, hot enough to make tin puddle like water. But step into shadow and you'll find yourself in a frozen wasteland where temperatures plunge to minus 180 degrees Celsius. We begin our descent toward this battered world, and immediately we notice something peculiar. There's no atmosphere to speak of, no protective blanket of air to cushion our approach. What Mercury calls an atmosphere is really just a wispy collection of atoms captured temporarily from space before being blown away again by the solar wind. The total mass of Mercury's entire atmosphere wouldn't fill a large swimming pool on Earth. This means there's no weather on Mercury, no clouds, no wind, no rain. Just the raw, unfiltered fury of the sun beating down on ancient rock. The lack of atmosphere also means that sound cannot exist here. If you could somehow stand on Mercury's surface and shout at the top of your lungs, the person next to you wouldn't hear a thing. It would be a world of perfect, absolute silence. As we approach the surface, the landscape reveals its secrets. Vast impact basins stretch to the horizon, scars from collisions so violent they shook the entire planet. The Caloris Basin, one of the largest impact craters in Theds before solar system, spree us like a frozen sea of destruction. When the object that created this basin struck Mercury billions of years ago, the impact was so powerful it sent shockwaves completely through the planet, creating strange rippled terrain on the exact opposite side of the world. Think about that for a moment. An impact so violent that the entire planet rang like a bell, the surface buckling and warping from forces transmitted through thousands of kilometers of solid rock. This is the kind of cosmic violence that shaped the early solar system, when planets were still young and the space between them was filled with debris left over from their formation. We descend through the surface now, passing through layers of rock that tell Mercury's story. This world is built differently from Earth. While our planet has a relatively small iron core surrounded by a thick rocky mantle, Mercury is mostly metal. Its iron core takes up about 3/4 of the planet's radius, making Mercury the second densest planet in the solar system after Earth. Why is Mercury so metal-rich? Scientists have proposed several theories. Perhaps Mercury was once much larger, similar to Earth in composition, but a catastrophic collision early in its history stripped away most of its rocky outer layers, leaving behind what's essentially a giant iron ball with a thin shell of rock. Alternatively, the intense heat from the young sun might have vaporized the lighter elements, leaving Mercury enriched in iron and other heavy metals. As we sink deeper into Mercury's interior, we feel the temperature rising. The outer layers are mostly silicate rock, baked and fractured by billions of years of thermal cycling. But as we approach the core, iron becomes the dominant element. The core itself is partially molten, generating a weak magnetic field that creates a tiny protective bubble around the planet. This magnetic field is only about 1% as strong as Earth's, but it's enough to deflect some of the solar wind and create small auroras at Mercury's poles. At the very center of Mercury, we might find a solid inner core where the pressure is so immense that iron remains solid despite temperatures of several thousand degrees. The boundary between the liquid and solid parts of the core is where Mercury's magnetic field is born, generated by convection currents of molten metal rising and falling in the planet's depths. Emerging from the other side of Mercury, we take one last look at this scorched world. Despite being the closest planet to the Sun, Mercury isn't actually the hottest planet in our solar system. That distinction belongs to our next destination, A world so shrouded in mystery and toxicity that it took decades for scientists to peer through its clouds and understand the hellish landscape hidden beneath. We leave Mercury behind and travel deeper into the inner solar system, toward a world that appears from space like a brilliant pearl, shining brighter than any star in Earth's sky. This is Venus, our so-called sister planet, a world that seems beautiful from a distance, but hides secrets that would make even the most hardened explorer think twice about visiting. Venus appears before us, wrapped in a thick blanket of clouds that completely obscure the surface. These aren't the white, fluffy water clouds of Earth. These are clouds of concentrated sulfuric acid, corrosive enough to eat through metal, dense enough to completely block our view of the world below. The cloud deck extends from about 20 kilometers above the surface to nearly 70 kilometers high, creating a layer so thick that only 2% of sunlight ever reaches the ground. As we begin our descent into this toxic maze, we immediately understand why Venus has been such a challenge to explore. The Soviet Venera probes that landed on Venus in the 1970s and 1980s survived on the surface for mere minutes before being destroyed by the crushing pressure and corrosive atmosphere. The conditions here are so extreme that they push the very limits of what we consider possible for planetary environments. The clouds themselves are fascinating and terrifying in equal measure. They're organized into distinct layers, each with its own chemical composition and temperature. The upper clouds contain sulfuric acid droplets mixed with water vapor. The middle layers are rich in sulfur compounds that give Venus its distinctive yellowish appearance. The lower layers are so dense and hot that the sulfuric acid begins to break down, creating a chemical soup unlike anything found on Earth. But the real surprise about Venus's atmosphere isn't its composition, it's its motion. While Venus rotates on its axis once every 243 Earth days, making it the slowest spinning planet in the solar system, its upper atmosphere whips around the planet in just 4 days. This means the clouds are moving at speeds of over 300 kilometers per hour, driven by winds that scientists still don't fully understand. This phenomenon, called superrotation, creates one of the most dynamic atmospheric systems in the solar system. The upper atmosphere is essentially decoupled from the solid planet below, spinning like a separate shell driven by forces that remain mysterious even today. It's as if the atmosphere has decided to ignore the planet's leisurely rotation and dance to its own rhythm instead. As we descend deeper into Venus's atmosphere, the pressure begins to build dramatically. What starts as a gentle squeeze gradually becomes a crushing embrace that would flatten any human instantly. By the time we reach the surface, the atmospheric pressure is 92 times greater than Earth's sea level pressure. That's equivalent to being nearly a kilometer underwater in Earth's oceans, deep enough to crush a submarine. The atmosphere itself is 96% carbon dioxide, creating the most extreme greenhouse effect known in our solar system. This thick blanket of carbon dioxide traps heat so efficiently that surface temperatures reach 470 degrees Celsius. That's hot enough to melt lead, hot enough to make some metals glow red hot. And unlike Mercury, where you could escape the heat by moving into shadow, Venus maintains this temperature everywhere, at the equator and at the poles, during the day and during the night. The thick atmosphere distributes heat so effectively that there are virtually no temperature variations across the entire planet. It's a world where the concept of weather, as we understand it, simply doesn't exist. No seasons, no cool nights, no refreshing breezes. Just endless, crushing heat that never varies and never stops. We continue our descent through layer after layer of this hostile atmosphere, and finally, the surface of Venus begins to emerge through the orange haze. What we see is a landscape unlike anything on Earth, yet strangely familiar at the same time. Vast volcanic plains stretch to the horizon, covered in frozen lava flows that tell the story of a world shaped entirely by volcanic activity. The surface of Venus reveals itself like a fever dream made manifest. Enormous shield volcanoes rise from the plains, some of them dwarfing anything Earth has ever produced. These aren't the familiar cone-shaped peaks we know from our own world. These are massive, broad mountains, built from countless eruptions over millions of years, their flanks spreading across hundreds of kilometers like frozen waves in a sea of stone. Unlike Earth, where plate tectonics constantly reshapes the surface, Venus appears to be a single, solid shell. There are no moving continents here, no ocean trenches, no mountain ranges pushed up by colliding land masses. Instead, Venus seems to periodically resurface itself through catastrophic volcanic episodes that cover the entire planet in fresh lava. The current surface is relatively young in geological terms, perhaps only 500 million years old, suggesting that at some point in Venus's recent past, the entire world was a molten hellscape. We descend through this surface now, passing through layers of volcanic rock that tell a story of incredible geological violence. The composition is similar to Earth's basalt, rich in iron and magnesium, but the structures are alien. Without the cooling effect of water or the organizing influence of plate tectonics, Venus's geology follows rules that Earth abandoned billions of years ago. As we sink deeper into Venus's interior, we pass through what might be the planet's crust and mantle. The internal structure is probably simpler than Earth's, without the complex layering created by subduction zones and continental drift. The mantle is likely a thick shell of hot, flowing rock, similar to Earth's mantle but without the dynamic circulation patterns that drive our planet's surface renewal. Deeper still, we approach Venus's core, a mystery wrapped in questions that scientists are still trying to answer. Venus should have an iron core similar to Earth's, and probably does, but something is different here. Venus has no magnetic field, which suggests that either its core is completely solid, completely liquid, or rotating too slowly to generate the electrical currents necessary for a magnetic dynamo. The lack of a magnetic field has profound consequences for Venus's interaction with space. Without this invisible shield, the solar wind strikes Venus's upper atmosphere directly STR, slowly ipping away lighter elements over geological time. This might be part of the reason why Venus lost whatever water it once had, leaving behind the bone-dry desert world we see today. The core temperatures probably reach 5,000 degrees Celsius, similar to Earth's core, but the pressure is slightly lower due to Venus's smaller size. If there is convection in the core, it's not organized enough to generate a coherent magnetic field, leaving Venus naked to the cosmic elements. Emerging from the far side of Venus, we look back at this world of extremes with a mixture of fascination and horror. Venus is a cautionary tale written in sulfuric acid and molten rock, a reminder of what can happen when a planet's climate spirals completely out of control. Scientists believe Venus might once have had oceans like Earth, but a runaway greenhouse effect boiled them away billions of years ago, leaving behind the furnace we see today. Our next destination couldn't be more different. We're heading home, to the one world in our solar system where the impossible has happened, where liquid water flows freely across the surface, where an atmosphere nurtures rather than destroys, where life has taken hold and flourished in ways that still boggle the scientific mind. Earth appears before us like a jewel suspended in the cosmic darkness, blue and white and brown swirling together in patterns that shift by the hour. From space, you can see weather systems forming and dissipating, hurricanes spinning like cosmic pinwheels, the Terminator line between day and night sweeping across continents and oceans. This is the only world we know where clouds are made of water instead of sulfuric acid, where the atmosphere prot than Krushek's rathers, where temperatures allow for the delicate chemistry that creates and sustains life. We begin our descent toward Earth, and unlike our previous destinations, this world greets us with a thick but breathable atmosphere. The air is mostly nitrogen and oxygen, with just enough the carbon dioxide to keep planet warm through a gentle greenhouse effect, but not so much that it creates the runaway heating that transforms Venus into hell. As we pass through the upper reaches of Earth's atmosphere, we encounter the mesosphere, where temperatures drop to their lowest point and strange, silvery clouds called noctilucent clouds form from ice crystals so high and thin they're invisible during the day, but glow like ghostly threads at twilight. Below this, the stratosphere welcomes us with its precious cargo of ozone molecules that absorb deadly ultraviolet radiation from the sun, creating an invisible shield that makes life possible on the surface below. Without this ozone layer, Earth would be as sterile as Mars, baked by radiation that would prevent complex molecules from forming and persisting. The ozone exists in a delicate balance, created by the interaction between oxygen molecules and solar radiation, maintained by natural processes that have operated for hundreds of millions of years. The troposphere embraces us next, the layer where all of Earth's weather happens. Here we pass through towering thunderstorms that stretch from near the surface all the way to the stratosphere, their tops flattened into anvil shapes by the temperature inversion above. Lightning flashes within these massive systems, each bolt carrying more electrical energy than most power plants generate, creating the nitrogen compounds that fertilize the soil and support the incredible diversity of life below. As we approach Earth's surface, that diversity becomes overwhelming. Mountain ranges thrust upward from the crust, their peaks carved by ice and wind and flowing water. The Himalayas continue rising as the Indian subcontinent crashes into Asia at the stately pace of centimeters per year. Deep ocean trenches plunge downward, the Mariana Trench reaching depths that would swallow Mount Everest with kilometers to spare. Deserts spread across continents, their sand dunes sculpted by winds into patterns that shift with the seasons. Rainforests pulse with life, their canopies hiding ecosystems so complex that scientists discover new species regularly. Ice caps gleam white at the poles, storing water that fell as snow thousands of years ago, preserving ancient atmospheres in bubbles trapped within the ice. This is a world shaped by the interplay between solid earth, liquid water, and gaseous atmosphere, all mediated by the presence of life itself. Life doesn't just inhabit Earth, it actively shapes the planet's environment, creating the oxygen we breathe, moderating the climate through complex feedback loops, even influencing the composition of rocks and minerals. We descend beneath the ocean's surface now, passing through layers of water that grow darker and colder with depth. sunlight penetrates only the first 200 meters, creating the euphotic zone where photosynthesis powers the base of the marine food web. Below this, the twilight zone stretches down to 1,000 meters, where strange creatures create their own light through bioluminescence, living constellations in the perpetual darkness. Deeper still, we enter the midnight zone, where the pressure would crush any unprotected human instantly, but where life persists in forms so alien they seem like visitors from another planet. Giant tube worms cluster around hydrothermal vents, deriving energy not from sunlight but from the chemical reactions of superheated water rich in minerals from Earth's interior. This deep sea life might represent the closest thing we have to truly alien biology, showing us what life might look like on worlds where sunlight never penetrates us, revealing the dynamic rates the ocean floor spreads beneath nature of our planet's surface. At mid-ocean ridges, new oceanic crust forms as magma wells up from the mantle below, pushing the seafloor apart at rates measured in centimeters per year. At subduction zones, old oceanic crust slides beneath continental plates, melting and recycling back into the mantle in a process that has operated for billions of years. We sink through the oceanic crust now, passing through layers of basalt formed at underwater volcanic ridges, then through the continental crust with its complex mixture of igneous, sedimentary, and metamorphic rocks. Each layer tells part of Earth's story. Ancient seas that evaporated, leaving salt deposits, volcanic eruptions that buried entire landscapes, mountain-building episodes that folded rock like paper. The boundary between crust and mantle marks a fundamental transition in Earth's structure. Below this point, we enter a realm of hot, slowly flowing rock that makes up the bulk of our planet's volume. The upper mantle behaves like a viscous fluid over geological timescales, flowing in vast convection currents that drive the movement of tectonic plates at the surface. These mantle currents are powered by heat from two sources: the decay of radioactive elements scattered throughout the rock, and the primordial heat left over from Earth's violent formation 4.6 billion years ago. As we descend deeper, the pressure builds to levels that transform the very structure of matter. Minerals that are stable at the surface become unstable under these conditions, their atoms rearranging into denser configurations. The transition zone between the upper and lower mantle is marked by dramatic changes in mineral structure, creating layers with different densities and properties. Some geologists think this boundary might act like a barrier, preventing material from the upper mantle from mixing freely with the lower mantle, creating chemical differences that persist over billions of years. The lower mantle extends down nearly 3,000 kilometers, its rock gradually becoming hotter and denser until we reach the core mantle boundary. Here, at a depth of 2,900 kilometers, we encounter one of the most dramatic transitions in the solar system. The temperature jumps by over 1,000 degrees Celsius across a boundary just a few kilometers thick, and the material changes from hot rock to liquid metal. Earth's outer core greets us with currents of molten iron and nickel flowing at velocities of kilometers per year. These flows, driven by convection and the planet's rotation, generate electrical currents that create Earth's magnetic field. This field extends far into space, forming the magnetosphere that deflects the solar wind and protects our atmosphere from being stripped away like Mars's atmosphere was billions of years ago. The dynamics of the outer core are incredibly complex, with the flowing metal organizing itself into patterns that scientists are still trying to understand. The The magnetic field reverses periodically, with north and south magnetic poles switching places in events that leave their signature in cooling lava and sedimentary rocks. These reversals happen irregularly, sometimes every few 100,000 years, sometimes not for millions of years. We continue our descent through the outer core, feeling the temperature climb toward 5,000 degrees Celsius, as hot as the surface of the sun. The pressure here exceeds 3 million times atmospheric pressure, creating conditions that exist nowhere else in the solar system except in the cores of other terrestrial planets. Finally, we reach Earth's inner core, a solid sphere of iron and nickel kept solid by pressure so intense it overcomes even these extreme temperatures. This innermost region of our planet rotates slightly faster than the rest of Earth, creating complex interactions with the outer core that influence the generation of the magnetic field. The inner core is growing slowly as the outer core cools and crystallizes, releasing latent heat that helps power the convection currents above. This process has been going on for billions of years and will continue for billions more, gradually changing the structure of Earth's deep interior in ways we're only beginning to understand. Emerging on the far side of Earth, we pause to appreciate what we've just experienced. This blue marble hanging only world we know where complexity in space is the has emerged from simplicity, where chemistry has become biology, where matter has organized itself into forms capable of contemplating their own existence. But our cosmic journey is far from over. We're heading outward now, past the frost line where water freezes and the architecture of worlds changes dramatically. Our next destination is a planet that once might have been as hospitable as Earth, but lost its atmosphere and its dreams of harboring life. This is Mars, the red planet, a world of ancient riverbeds and vanished oceans, where the ghosts of what might have been still haunt every crater and canyon. Mars appears before us like a rusty sphere suspended in the darkness. Smaller than Earth, but somehow more haunting, more mysterious. From space, the red planet reveals itself as a world caught between what it once was and what it has become. Ancient river valleys snake across continents, their dried channels telling stories of water that flowed billions of years ago. Polar ice caps gleam white against the rusty landscape, holding within their frozen layers the only substantial water remaining on a world that might once have rivaled Earth in its hospitality to life. As we approach Mars, the first thing that strikes you is how thin and fragile its atmosphere appears. Unlike Earth's substantial blanket of air or Venus's crushing envelope of gas, Mars possesses barely a whisper of atmosphere. The atmospheric pressure at the surface is less than 1% of Earth's, so tenuous that liquid water simply cannot exist on the surface. It would either freeze solid or boil away into vapor, depending on the temperature and season. This wispy atmosphere is mostly carbon dioxide, with traces of nitrogen and argon. But there's so little of it that it provides virtually no greenhouse warming. Surface temperatures average minus 60 degrees Celsius, though they can rise above freezing at the equator during summer days before plunging back below freezing at night. Mars is a world of constant winter, where even the warmest days would feel bitterly cold to any earthly visitor. We begin our descent through this thin veil of atmosphere, and immediately we notice something extraordinary happening below us. Dust devils dance across the surface, towering vortices that can reach several kilometers high, visible even from our lofty vantage point. These aren't gentle whirlwinds. They're massive, tornado-like structures created by the sun heating the ground unevenly, causing columns of air to rise and spin with surprising violence. During certain seasons, these dust storms can grow beyond anything Earth has ever experienced. They can engulf the entire planet, turning day into twilight and lasting for months at a time. The dust is incredibly fine, like talcum powder, and it gets into everything. It coats every surface, fills every crevice, and hangs in the thin air for weeks after the storms pass. This dust gives Mars its characteristic red color, iron oxide that has been ground down and scattered across the planet by billions of years of wind erosion. The surface of Mars spreads out beneath us like a geological textbook written in stone and dust. The northern hemisphere is dominated by smooth lowland plains, ancient ocean basins that scientists believe once held vast seas of liquid water. These Vastitas Borealis plains are among the flattest surfaces in the solar system, punctuated only by occasional impact craters and volcanic features. The southern hemisphere tells a different story entirely, presenting heavily cratered highland terrain that preserves impacts from the solar system's violent youth. The boundary between these two regions is one of the most dramatic topographical features in the solar system. The dichotomy boundary represents an elevation change of several kilometers, creating a cliff system that stretches around nearly half the planet. This massive divide might have been created by a colossal impact early in Mars's history, or it could represent the ancient shoreline of a planet-wide ocean that covered the northern lowlands billions of years ago. We saw over Olympus Mons, the largest volcano in the solar system, a shield volcano so massive it defies earthly comparison. This mountain rises 21 kilometers above the surrounding plains, nearly 2.5 times the height of Mount Everest, with a base that spans 600 kilometers. The summit contains a caldera 85 kilometers wide, large enough to swallow entire cities. This volcano was built over billions layers of eruptions, each one adding another of years by countless lava to the growing mountain. The sheer size of Olympus Mons tells us something profound about Mars's geological history. Unlike Earth, where plate tectonics would have moved volcanic islands away from their hotspots, Mars lacks moving plates. This allowed single volcanoes to remain stationary over their magma sources for billions of years, growing larger and larger without being carried away by continental drift. The volcano is a monument to geological time, a structure that could only exist on a world where the crust remains fixed in place. Nearby, the Tharsis region hosts 3 other massive volcanoes, all of them extinct now, all of them evidence of a time when Mars was geologically vibrant and active. These mountains represent some of the most recent volcanic activity on Mars, though recent in geological terms means hundreds of millions of years ago. The planet's smaller size meant it cooled faster than Earth, and its geological engine gradually wound down until volcanic activity ceased entirely. We descend toward Valles Marineris, a canyon system so vast it makes Earth's Grand Canyon seem like a small scratch in comparison. This enormous rift stretches over 4,000 kilometers across the Martian surface, roughly 1/5 of the planet's circumference. In places, it reaches 7 kilometers deep and 200 kilometers wide. If Valles Marineris existed on Earth, it would stretch from New York to Los Angeles, carving a gash across the entire continent. The canyon was probably formed billions of years ago when the Tharsis region was uplifting, stretching and cracking the crust like pulling apart a piece of bread dough. As we fly through the canyon depths, we pass that record through layers of rock, billions of years of Martian history, ancient river channels cut through the canyon walls, evidence of a time when liquid water flowed freely across Mars, carving features that dwarf anything Earth has ever experienced. Some of these channels are enormous, suggesting catastrophic floods that release more water in days or weeks than the Mississippi River carries in centuries. Scientists believe that underground ice might have melted suddenly, perhaps from volcanic heating, releasing vast quantities of water that carved these massive channels in geological instants. The scale of these ancient floods hints at a Mars that was once dramatically different from the frozen desert we see today. We continue our descent, sinking through the Martian surface into the planet's crust. The crust here is thicker than Earth's, perhaps 50 kilometers thick on average, composed mostly of volcanic basalt in the lowlands and older, more complex rock formations in the highlands. Unlike Earth's dynamic crust with its constantly moving plates, Mars possesses a single solid shell that has remained largely static for billions of years. This geological stability means that Mars preserves surface features billions of years old, creating a planetary museum that records events from the very beginning of the solar system. Impact craters that would have been erased by plate tectonics and erosion on Earth remain perfectly preserved on Mars, telling stories of cosmic bombardment that occurred when the planets were young and space was filled with debris. As we sink deeper into the Martian interior, we pass through the mantle, a thick layer of silicate rock similar to Earth's mantle, but cooler and more rigid. Mars cooled faster than Earth because of its smaller size, and the mantle no longer flows in the vigorous convection currents that drive plate tectonics on our home planet. The lack of internal heat also means Mars has no active volcanism anymore, no magnetic field generated by a liquid core, and no geological processes capable of recycling carbon dioxide back into the atmosphere. We approach Mars's core, and here scientists face intriguing mysteries. Mars once possessed a strong magnetic field, evidenced by magnetized rocks in the ancient southern highlands that preserve the signatures of that long-vanished field. But the magnetic field disappeared roughly 4 billion years ago, leaving Mars defenseless against the solar wind that gradually stripped away its atmosphere. The core is probably made of iron and nickel like Earth's core, but it must be either completely solid or completely liquid, unable to generate the convection currents needed for a magnetic dynamo. Some scientists believe the core might be partially liquid but not convecting because it's either too cold or contains too much sulfur, which lowers the melting point and changes the dynamics of heat transfer. The core extends roughly half of Mars's radius, smaller proportionally than Earth's core, and reaches temperatures that might peak at only 2000 degrees Celsius, much cooler than Earth's molten center. The pressure is also much lower, perhaps only a few 100,000 times atmospheric pressure rather than the millions of atmospheres at Earth's core. As we pass through the core and emerge on the far side of Mars, we're left with a profound sense of loss. This is a world that might have developed life billions of years ago, when it possessed liquid water on its surface, a thicker atmosphere, and a warmer climate. But without the geological processes that maintain Earth's habitability, Mars gradually lost its atmosphere to space, its water froze or escaped, and its climate grew. Mars cold and bar represents lost potential. A planet that started with many of the same advantages as Earth, but lacked the size and internal heat necessary to maintain them over geological time. The rusty surface we see today is a monument of how fragile the planetary death. A reminder conditions are that allow worlds to remain habitable over billions of years. But our journey through the solar system is far from over. We're heading outward now, past the asteroid belt that marks the boundary between the terrestrial planets and the gas giants. Our next destination exists on a scale so vast it challenges human comprehension, a world so massive that all the other planets combined could fit within its boundaries with room to spare. Jupiter appears before us like a banded jewel, its great red spot glaring like a cosmic eye that has watched over the solar system for centuries. This isn't a planet in any sense that we understand from our experience with rocky worlds. This is something entirely different, a failed star that never quite achieved the mass necessary to ignite nuclear fusion. A world composed almost entirely of the same hydrogen and helium that fills the spaces between stars. As we approach Jupiter, the sheer scale becomes overwhelming. This giant world contains more than twice the mass of all other planets combined, and its gravitational influence extends throughout the outer solar system, shepherding asteroids, capturing comets, and maintaining the orbital stability that has allowed life to flourish on Earth. Jupiter is both protector and destroyer, deflecting dangerous objects away from the inner planets, while also preventing the formation of another world in the asteroid belt through its powerful gravitational stirring. The approach to Jupiter takes us past its magnificent retinue of moons, a miniature solar system in its own right. We catch glimpses of Io, painted in sulfurous yellows and oranges, the most volcanically active body in the entire solar system. Europa appears wrapped in a shell of ice that may conceal an ocean larger than all of Earth's seas combined. Ganymede looms massive and ancient, larger than the planet Mercury, while Callisto shows us a surface so heavily cratered it looks like a cosmic archaeological site. But we're not stopping at these moons, fascinating as they are. We're diving straight into Jupiter itself, into atmospheric layers that grow stranger and more exotic with every kilometer of descent. The outer edges of Jupiter's atmosphere greet us first, so tenuous that it's difficult to say exactly where space ends and the planet begins. But soon we're enveloped in clouds, and the first thing that strikes you is the incredible organization of the atmospheric structure. Bands of clouds stretch horizontally around the planet, each one a river of atmosphere flowing at different speeds and altitudes. These bands are created by Jupiter's rapid rotation. The planet spins once every 10 hours, faster than any other world in the solar system. This creates powerful Coriolis forces that organize the atmosphere into distinct zones and belts, with bright zones representing regions where gas is rising and cooling, and darker belts marking areas where gas is descending and warming. The winds here are ferocious, reaching speeds that would tear apart any earthly structure. In some regions, atmospheric rivers flow at over 600 kilometers per hour, creating jet streams that make Earth's most powerful winds seem like gentle breezes. These aren't temporary weather systems like hurricanes that form and dissipate over days or weeks. These are permanent features of Jupiter's atmosphere, maintained by the planet's rotation and internal heat generation. The Great Red Spot looms before us, a storm system that has persisted for at least 3 centuries, possibly much longer. This anticyclonic tempest is larger than Earth itself, with winds at its edges reaching 400 kilometers per hour. The spot's distinctive red color comes from complex organic molecules created when sunlight breaks down methane and ammonia in the upper atmosphere. though the exact chemistry remains mysterious even today. We plunge into this ancient storm, and the experience defies description. Vertical wind shears create turbulence that would instantly destroy any aircraft ever built. Lightning flashes illuminate the clouds from within, but these aren't the brief sparks we know from Earth. These are sustained electrical discharges that can last for minutes, carrying energies that dwarf terrestrial lightning by factors of thousands. The storm extends deep into Jupiter's interior, perhaps hundreds of kilometers down, powered by heat rising from the planet's core and the complex dynamics of atmospheric circulation. As we continue our descent through Jupiter's atmosphere, the pressure begins to build in ways that transform our understanding of what matter can become. At depths of several hundred kilometers, where the pressure reaches several times Earth's surface pressure, something remarkable begins to happen. The hydrogen that fills Jupiter's atmosphere starts to behave less like a gas and more like a liquid. This transition isn't sharp or sudden, like water boiling in a pot. Instead, it's a gradual change where the density slowly increases, the molecules move closer together, and the distinction between gas and liquid becomes meaningless. We're entering Jupiter's hydrogen ocean, a sea that has no surface, no waves, no boundaries, just an endless expanse of liquid hydrogen that extends for thousands of kilometers in all directions. This ocean exists under conditions that cannot be replicated anywhere on Earth. The pressure here exceeds anything in our deepest ocean trenches, while temperatures climb toward levels that would melt most metals. We're swimming through liquid hydrogen while surrounded by an envelope of gaseous hydrogen above and denser phases of matter below. It's an environment so alien that our earthly experience provides no reference points for understanding it. We sink deeper through this hydrogen sea, and at depths of roughly 20,000 kilometers, where the pressure reaches millions of times Earth's atmospheric pressure, we encounter something even more extraordinary. The hydrogen around us undergoes another phase transition, transforming into a state of matter that exists nowhere else in the solar system except in the cores of the giant planets. Under these crushing pressures, hydrogen atoms are squeezed so tightly together that their electrons are stripped away, creating a fluid that conducts electricity like liquid metal. This is metallic hydrogen, a substance that scientists have tried desperately to create in Earth laboratories, but have only managed to produce for microseconds before it explodes. Here in Jupiter's depths, metallic hydrogen exists in quantities that boggle the imagination, forming oceans of electrically conductive fluid that generate the planet's powerful magnetic field. This metallic hydrogen region extends for thousands of kilometers through Jupiter's interior, and it's here that one of the solar system's most impressive phenomena takes shape. As Jupiter spins on its axis every 10 hours, this conducting ocean generates electrical currents that create a magnetic field 20,000 times stronger than Earth's. This field extends millions of kilometers into space, creating a magnetosphere so vast it would appear larger than the full moon if we could see it from Earth. The magnetic field traps charged particles from the solar wind and accelerates them to incredible energies, creating radiation belts so intense they would kill an unprotected human in minutes. The interaction between this field and Jupiter's moons creates some of the most spectacular displays in the solar system, with electrical currents flowing between Jupiter and Io, carrying more power than all of Earth's power plants combined. We continue our descent through the metallic hydrogen, feeling temperatures climb towards 10,000 degrees Celsius, as hot as the surface of the sun. The pressure here approaches 40 million times Earth's atmospheric pressure, creating conditions so extreme that our understanding of how matter behaves begins to break down. We're approaching the realm where quantum effects become important, where the familiar laws of chemistry and physics require modification to account for the bizarre behavior of matter under such extraordinary conditions. And still we descend, approaching the mysterious heart of Jupiter, the core that has puzzled scientists for decades. Early models suggested a small, rocky core, perhaps 10 to 15 times Earth's mass, composed of heavy elements that sank to the center during Jupiter's formation. But recent data from NASA's Juno spacecraft has revealed something far more complex and intriguing. Instead of a well-defined solid core, Jupiter appears to possess what scientists call a fuzzy or diluted core, a region where rock and metallic hydrogen are mixed together in ways that challenge our understanding of planetary formation. This core region might extend across nearly half of Jupiter's radius, larger than the entire planet Earth. Yet it's not a solid boundary, but rather a gradual transition from one type of matter to another. The temperatures at Jupiter's center might reach 30,000 degrees Celsius, hot enough to rival the cores of some stars, while pressures could exceed 50 million Earth atmospheres. These are conditions so extreme that they push the boundaries of what we can model or predict, entering regimes where the behavior of matter becomes governed by quantum mechanical effects we're only beginning to understand. As we emerge from the far side of Jupiter, we carry with us the memory of having touched conditions that exist nowhere else in our solar system. We've witnessed the birth of magnetic fields in oceans of metallic hydrogen, experienced pressures that compress matter into states that challenge the very definitions of solid and liquid, and descended through atmospheric layers that demonstrate the incredible diversity of environments that can exist within a single world. Jupiter stands as a monument to the power of gravity and the strange behavior of matter under extreme conditions. It's a world that operates according to physics pushed to their limits, a laboratory for studying phenomena that exist nowhere else within our reach. But it's also a guardian, using its massive gravitational influence to shape the architecture of our entire solar system and protect the inner planets from bombardment by comets and asteroids. Our journey continues outward now, toward a world that rivals Jupiter in beauty, if not in size. Saturn awaits us, adorned with the most spectacular ring system in the solar system. A world that demonstrates how gravity can organize matter into structures of breathtaking elegance and complexity. The jeweled planet beckons, promising wonders that will challenge everything we thought we knew about how worlds can adorn themselves with cosmic jewelry spanning hundreds of thousands of kilometers, yet remaining thinner than a skyscraper is tall. Saturn appears before us like a masterpiece of cosmic artistry, wrapped in rings so delicate and intricate they seem almost too perfect to be real. From our approach, the planet itself appears as a pale golden orb, its atmosphere more subdued than Jupiter's dramatic bands, yet somehow more elegant in its restraint. The rings catch and scatter sunlight like billions of tiny mirrors, creating a display that has captivated human imagination since Galileo first glimpsed them through his primitive telescope centuries ago. As we draw closer, the true majesty of Saturn's ring system reveals itself in all its impossible complexity. What appears from Earth as solid bands of light resolves into thousands upon thousands of individual ringlets, each one a separate stream of orbiting particles following their own gravitational dance around the planet. The Cassini division opens before us like a cosmic highway. A gap 4,000 kilometers wide that separates the bright A and B rings, kept clear by the gravitational influence of Saturn's moon Mimas orbiting far beyond. We pass through the outer reaches of the ring system, and the experience defies every expectation. These aren't solid structures at all, but vast collections of ice and rock fragments, each piece following its own orbital path with mathematical precision. Some particles are no larger than grains of sand, glittering like cosmic snow in the reflected sunlight. Others are house-sized boulders, tumbling slowly as they circle Saturn in an eternal procession that has continued for millions of years. The rings themselves are impossibly thin, spanning hundreds of thousands of kilometers in diameter, yet measuring less than a kilometer thick in most places. It's as if someone had taken a sheet of paper and stretched it across a distance that would span from Earth to the Moon, creating a structure so delicate that a slight gravitational perturbation could scatter it to the solar winds, yet so stable that it has persisted for eons. We leave the ring plane behind and approach Saturn's cloud tops, immediately noticing how different this world appears from its larger cousin Jupiter. The atmospheric bands are there, the familiar pattern of zones and belts created by rapid rotation and atmospheric circulation. But they're hazier, more muted, as if viewed through a cosmic fog. The colours are subtler too, pale yellows and creams and tans that speak of a cooler, more distant world receiving only a quarter of the sunlight that illuminates Jupiter's storms. Saturn's distance from the Sun creates an environment of perpetual winter. The cloud tops hover at temperatures of -140 degrees Celsius, cold enough to freeze most atmospheric gases solid. Yet the planet's interior generates enough heat to drive some of the most powerful winds in the solar system. At the equator, atmospheric currents race around Saturn at speeds exceeding 1,800 kilometers per hour, faster even than Jupiter's mighty jet streams. These super-rotating winds create phenomena that exist nowhere else in the solar system. At Saturn's North Pole, atmospheric currents have organized themselves into a perfect hexagonal pattern, a geometric storm system where each side of the hexagon spans distances greater than Earth's diameter. This bizarre formation has persisted for decades, maintained by atmospheric dynamics that scientists are still struggling to understand. It's as if Saturn's atmosphere has learned to think geometrically, creating order from the chaos of turbulent gas flows. We begin our descent into Saturn's atmosphere, and the familiar pattern of increasing pressure and temperature begins. The upper clouds are composed primarily of ammonia ice crystals, creating those pale, hazy layers we observed from space. Below them, deeper atmospheric layers contain ammonium hydrosulfide clouds, and deeper still, water ice clouds form in regions where the pressure and temperature allow water vapor to condense. The chemistry of Saturn's atmosphere mirrors Jupiter's in many ways, mostly hydrogen and helium with traces of methane, ammonia, and other compounds. But the colder temperatures create different cloud condensation patterns. The haze that gives Saturn its subdued appearance comes from high-altitude hydrocarbon smog, created when ultraviolet light from the sun breaks down methane molecules and reassembles them into more complex organic compounds. As we descend deeper into Saturn's atmosphere, we witness lightning storms that dwarf their terrestrial counterparts. These aren't the brief flashes we know from Earth, but sustained electrical displays that can persist for hours, illuminating vast regions of Saturn's interior with energies that exceed the power output of entire cities. The radio emissions from these storms are so intense they can be detected by spacecraft throughout the outer solar system. Around 1,000 kilometers deep, we encounter the transition from gaseous to liquid hydrogen, just as we did within Jupiter. But Saturn's lower mass means this transition occurs at different pressures and temperatures, creating a hydrogen ocean with its own unique characteristics. The boundary between gas and liquid is even more gradual here, a smooth transition that demonstrates how matter behaves when gravitational forces organize it on planetary scales. We sink through thousands of kilometers of liquid hydrogen, experiencing pressures that climb steadily toward the exotic realm where hydrogen transforms into its metallic state. At roughly 30,000 kilometers deep, where pressures exceed 60 million Earth atmospheres, we enter Saturn's metallic hydrogen region, a conducting ocean that generates the planet's magnetic field through the same dynamo process that powers Jupiter's electromagnetic phenomena. Saturn's magnetic field is weaker than Jupiter's, only about 20 times stronger than Earth's field, but it creates its own magnificent displays of electromagnetic artistry. The field interacts with charged particles from Saturn's moons, particularly Enceladus, which spews water vapor and ice particles into space through geysers at its south pole. These particles become ionized and trapped in Saturn's magnetosphere, creating auroral displays that dance across the planet's polar regions in ultraviolet wavelengths invisible to human eyes, but spectacular when viewed through appropriate instruments. The metallic hydrogen ocean extends for thousands of kilometers through Saturn's interior, a realm of conducting fluid where temperatures climb toward 15,000 degrees Celsius and pressures approach conditions that exist in the cores of some stars. We're swimming through matter in a state that pushes the boundaries of our understanding, where the familiar distinctions between different phases of matter become meaningless. Deep within Saturn's core region, we encounter the same mysteries that puzzle scientists studying Jupiter's interior. Recent gravitational measurements suggest that Saturn, like Jupiter, may possess a dilute or fuzzy core rather than a well-defined solid center. This core region might contain 10 to 20 times Earth's mass worth of heavy elements, rock, metals, and ices, but spread throughout a volume larger than Earth itself, rather than concentrated into a compact ball. The core temperatures might reach 20,000 degrees Celsius, while pressures could approach 80 million Earth atmospheres. These are conditions so extreme that they exist nowhere else in our solar system except possibly in the hearts of the other Essing matter giant planets, where Witten behave according to rules that require quantum mechanics to understand, where the very concept of distinct chemical elements begins to break down under the crushing weight of planetary formation. The formation of Saturn's core region remains one of the great puzzles in planetary science. Computer models suggest that during the planet's formation, massive impacts from other planetary embryos might have mixed core materials with the surrounding hydrogen and helium envelope, creating the diffuse structure we observe today. Alternatively, the core might have formed gradually through the slow settling of heavy elements over billions of years, a process that's still ongoing in the planet's deep interior. As we emerge from the far side of Saturn, we carry with us the memory having witnessed one of nature's most elegant demonstrations of how gravity can organize matter into structures of breathtaking beauty and complexity. The rings alone represent a masterpiece of celestial mechanics, billions of individual particles locked in orbital resonances that maintain their collective structure across geological timescales. But Saturn is more than just a beautiful spectacle. It's a laboratory for studying atmospheric dynamics under conditions that don't exist on Earth, a testing ground for theories about how magnetic fields are generated in planetary interiors, and a gravitational anchor that helps maintain the stability of the outer solar system. The planet's moons form their own complex ecosystem, with Titan's methane lakes and Enceladus's subsurface ocean potentially harboring environments where life might find a foothold. Our journey continues outward now, beyond the realm of the classical planets into territory that was unknown to ancient astronomers. We're heading toward the ice giants, worlds so distant and cold that they challenge our understanding of what planets can be. These are realms where water doesn't flow as liquid, but exists as exotic forms of ice, where methane falls as snow, and where magnetic fields behave in ways that defy our expectations. Uranus awaits us, the planet that rolls through space on its side, a world knocked askew by some ancient catastrophe that left it tumbling through its orbit like a cosmic bowling ball. This pale blue-green sphere represents our first encounter with a fundamentally different class of planet. One where the familiar hydrogen and helium that dominate Jupiter and Saturn give way to more complex mixtures of water, methane, and ammonia compressed into states that exist nowhere else in our solar system. As we approach Uranus, the first thing that strikes you about this distant world is its peculiar orientation. While every other planet spins roughly upright like a top, Uranus rotates on its side with an axial tilt of 98 degrees. This means that for part of its 84-year orbit around the Sun, one pole points directly toward our star, while the other experiences decades of continuous darkness. Then, 42 years later, the situation completely reverses. AI's rotation creates seasonal, this side view patterns unlike anything else in the solar system. Imagine a world where summer at one pole lasts for 21 Earth years, followed by 21 years of spring, then 21 years of autumn, then 21 years of winter. The temperature differences between the sunlit and shadowed hemispheres create atmospheric dynamics that operate on timescales measured in decades, rather than the days or weeks we're familiar with from terrestrial weather. The cause of Uranus's unusual tilt remains one of the great mysteries of planetary formation. The most widely accepted theory suggests that during the chaotic early period of solar system formation, Uranus suffered a collision with another planetary-sized object. This impact would have been so violent that it knocked the entire planet onto its side, possibly also stripping away some of its original atmosphere and creating the unusual magnetic field configuration we observe today. From our approach, Uranus appears remarkably bland compared to the dramatic cloud bands of Jupiter and Saturn. The planet presents an almost featureless blue-green disk, its color created by methane in the upper atmosphere that absorbs red light and reflects blue and green wavelengths back to space. The lack of visible cloud structures doesn't mean Uranus is inactive. It simply means that whatever weather systems exist are hidden beneath layers of high-altitude haze. We begin our descent into Uranus's atmosphere, and immediately we notice how different the thermal environment is from the gas giants we visited. The upper atmosphere is incredibly cold, reaching temperatures of -220 degrees Celsius, making it the coldest planetary solar system. Unlike atmosphere in the Jupiter and Saturn, which raw heat thandiate more they receive from the Sun, Uranus generates very little internal heat, making it colder than it should be at its distance from our star. The atmosphere itself is mostly hydrogen and helium, like the gas giants, but with a much higher proportion of methane. As we descend through the relatively thin atmospheric layer, only a few thousand kilometers deep, we encounter something fundamentally different from what we found in Jupiter and Saturn. Instead of endless layers of hydrogen in various phases, we're entering a realm that scientists call the mantle, though it bears no resemblance to the rocky mantles of terrestrial planets. This is a hot, dense fluid composed of water, methane, and ammonia compressed under enormous pressures. Under the extreme conditions within Uranus, water doesn't behave like the familiar liquid we know. Instead, it exists as superionic ice, a bizarre state of matter where oxygen atoms are locked, crystalled in a Solian lattice, while hydrogen ions flow freely through that lattice like a liquid, conducting electricity in the process. This superionic ice ocean extends for thousands of kilometers through Uranus's interior, creating an environment so alien that we have no terrestrial analog for comparison. The temperatures here climb to several thousand degrees Celsius, while pressures exceed millions of Earth atmospheres. Yet the material around us maintains properties of both solid and liquid phases simultaneously. The electrical conductivity of this superionic ice ocean is thought to be responsible for Uranus's magnetic field, but that field itself presents another puzzle. Unlike the relatively orderly magnetic fields of Earth, Jupiter, and Saturn, Uranus's magnetic field is tilted 60 degrees from the planet's rotation axis and offset significantly from the center. As Uranus rotates, this misaligned field wobbles through space like a cosmic corkscrew, creating a magnetic environment unlike anything else in the solar system. We continue our descent through the superionic ice ocean, passing through regions where the pressure approaches 2 million Earth atmospheres and temperatures climb toward 5,000 degrees Celsius. The behavior of matter under these conditions challenges our understanding of how chemical bonds form and break under extreme pressure. We're witnessing materials that could only exist in the interiors of planets, substances that cannot be created or studied in any earthly laboratory. At the very center of Uranus, there might exist a small rocky core, perhaps half an Earth's mass of iron and silicate rock, compressed to incredible densities. Alternatively, there might be no distinct core at all, just a gradual transition to denser materials as we approach the planet's center. The uncertainty reflects how difficult it is to study planetary interiors from space, relying on gravitational measurements and theoretical models to infer what lies thousands of kilometers below the surface. The core region, if it exists as a distinct entity, would experience conditions that push matter to its limits. Temperatures might reach 10,000 degrees Celsius, while pressures could exceed 10 million Earth atmospheres. Under such extreme conditions, the very concept of distinct chemical compounds begins to break down as atoms are squeezed into configurations that don't exist anywhere else in our solar system. Emerging from Uranus, we carry with us the memory of having touched a fundamentally different kind of world. This ice giant represents a class of planet that may be among the most common in our galaxy, yet we know remarkably little about how such worlds form and evolve. The Voyager 2 flyby in 1986 provided our only close-up look at Uranus, a brief snapshot that raised more questions than it answered about this enigmatic world. The unusual properties of Uranus, its sideways rotation, offset magnetic field and lack of internal heat, suggest a formation history filled with violence and chaos. Understanding how such worlds develop and what processes shape their evolution is crucial for interpreting observations of similar planets to other stars. Ice, where round giants appear to be far more common than the gas giants we're familiar with in our own solar system. Our journey continues to its final destination, the most distant planet in our solar system since Pluto's reclassification as a dwarf planet. Neptune awaits us, a world of deep blue beauty and surprising activity despite its enormous distance from the Sun. This ice giant promises to show us how planetary atmospheres can remain dynamic and energetic even in the frozen outer reaches of our cosmic neighborhood. Neptune appears before us as a rich, vibrant blue sphere, its color deeper and more intense than Uranus, despite their similar atmospheric compositions. As we approach, we immediately see evidence of the dynamic activity that sets Neptune apart from its cousin. Great dark spots appear and disappear in the planet's atmosphere. Massive storm systems comparable to Jupiter's Great Red Spot, but far more transient, forming and dissipating over periods of years rather than centuries. White clouds of methane ice float high above the main cloud deck, casting shadows on the atmospheric layers below, like cosmic cotton balls suspended in an alien sky. These high-altitude clouds form when methane gas rises to the cold upper reaches of Neptune's atmosphere and condenses into ice crystals that reflect sunlight with brilliant intensity. But perhaps most remarkable of all are the winds. Despite receiving only 1/10,000th of the sunlight that Earth receives, despite being the most distant planet from our star's warming influence, Neptune generates wind speeds that are the fastest in the solar system. Atmospheric currents race around the planet at velocities exceeding 2,000 kilometers per hour, faster than the speed of sound on Earth. How Neptune generates the energy to drive these incredible winds remains one of the great mysteries of planetary science. The planet should be too cold and too far from the Sun to maintain such vigorous atmospheric activity. Yet observations consistently show storm systems and wind patterns that rival or exceed anything found on worlds much closer to our star. Like Jupiter and Saturn, Neptune radiates more heat than it receives from the Sun, suggesting that internal energy sources power its atmospheric dynamics. But the mechanisms remain poorly understood. We begin our descent into Neptune's dynamic atmosphere, and the structure proves similar to Uranus in many ways. A of hydrogen-thin envelope, relatively helium, and methane gives way to the characteristic supersonic ice mantle that defines the ice giant class of planets. But Neptune's greater mass means higher internal pressures and temperatures, creating subtle differences in how materials behave in the planet's interior. The magnetic field here shares the same puzzling characteristics we found at Uranus, tilted significantly from the rotation axis and offset from the center. This suggests that both ice giants generate their magnetic fields through processes fundamentally different from the dynamos operating in the gas giants or terrestrial planets. The supersonic ice that conducts electricity in these worlds creates magnetic field geometries that we're still struggling to understand. As we descend through Neptune's supersonic ice ocean, we experience the most extreme conditions of our entire journey through the solar system. The pressures here exceed anything we encountered in the other planets. while temperatures climb toward levels that rival stellar cores. We're witnessing matter compressed to densities that approach the theoretical limits of how tightly atoms can be packed together. Deep within Neptune's core region, there might exist a rocky center slightly larger than Earth, compressed to densities that make terrestrial rocks seem as light as foam. The core temperatures could reach 15,000 degrees Celsius, while pressures might exceed 20 million Earth atmospheres. These are conditions so extreme that they exist nowhere else in our solar system, representing the ultimate expression of how gravity can compress matter when given enough material to work with. The formation of Neptune and Uranus remains an active area of research, with computer models suggesting these worlds might not have formed where we find them today. Instead, they might have assembled closer to the Sun before migrating outward through gravitational interactions with Jupiter and Saturn. This migration could explain why ice giants are less massive than the gas giants. They formed in regions where less material was available and were pushed outward before they could capture the vast hydrogenized Jupiter envelopes that character in Saturn. As we emerge from Neptune and look back at this dynamic world, we complete our impossible journey through every planet in our solar system. From Mercury's scorched surface to Neptune's howling winds, we've witnessed the incredible diversity that exists within our cosmic neighborhood. Each world tells its own story of formation and evolution, of how matter organizes itself under different conditions of temperature, pressure, and gravitational influence. The 8 planets we visited represent just a tiny sample of the worlds that exist throughout our galaxy. Recent discoveries of exoplanets have revealed hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Super-Earths with masses several times greater than our homeworld, and planetary systems with architectures completely unlike our own solar system. Yet our journey through these familiar worlds has given us insights into the fundamental processes that shape all planets everywhere. We've seen how gravity sculpts matter into sphere, how rotations organizes atmospheric circulation, how internal heat drives geological activity, and how magnetic fields protect or fail to protect planetary atmospheres from the harsh radiation of space. Each planet we've touched exists as a natural laboratory, demonstrating physics under conditions we could never replicate on Earth. From the metallic hydrogen oceans of Jupiter to the supersonic ice mantles of the ice giants, we've witnessed matter behaving in ways that challenge our understanding and push the boundaries of what we thought possible. Our impossible voyage reminds us that we live in a universe of extraordinary diversity and beauty, where worlds beyond imagination orbit every star we see in the night sky. The solar system is our cosmic backyard, 8 worlds that share our sun and our history, each one a treasure trove of scientific discovery waiting to be fully explored. Tonight, as we drift away from Neptune's howling winds and look back across the vast expanse we've traveled, something profound settles in your consciousness. We've accomplished the impossible, touched worlds zihilate any spacecraft that were in microseconds, descended through realms where the very definitions of matter break down under pressures that exist nowhere else in creation. But here's what makes this journey truly extraordinary. Every detail we've experienced, every temperature we've felt, every pressure that would have crushed us, every chemical reaction we've witnessed, comes from real data gathered by actual human beings who dedicated their lives to understanding these distant worlds. The temperatures on Venus's surface, the composition of Jupiter's metallic hydrogen core, the wind speeds screaming across Neptune's frozen atmosphere. All of this knowledge was painstakingly assembled by scientists who sent robotic explorers across billions of kilometers of empty space. Consider the audacity of what we've actually done as a species. We've built machines capable of surviving launch from Earth, navigating through the vacuum of space for years or decades, and functioning in environments that would destroy them in seconds if their shielding failed. The Mariner probes that first revealed Mercury and Venus in the 1960s, the Viking landers that touched Martian soil in 1976, analyzing alien chemistry with instruments no larger than a briefcase, the Voyager spacecraft that performed their grand tour of the outer planets, sending back images that transformed distant points of light into actual worlds with weather and geology and moons of their own. These missions represent something almost miraculous about human curiosity. We built these explorers not because we had to, not because there was immediate practical benefit, but because we couldn't bear not knowing what was out there. We invested decades of work and billions of dollars to answer questions that had no guaranteed return except the satisfaction of understanding. Think about the Galileo spacecraft, which spent 8 years orbiting Jupiter, studying its moons and atmosphere before diving into the planet itself in a planned suicide mission. Or Cassini, which danced among Saturn's moons for 13 years, discovering geysers on Enceladus and methane lakes on Titan, before finally plunging into Saturn's atmosphere in 2017. These weren't just scientific instruments. They were our eyes and ears in places we could never go, extending human consciousness across the solar system. Every measurement they made, every photograph they captured, every spectrum they analyzed, contributes to the journey we've taken tonight. When we describe the crushing pressure of Jupiter, the bottom's atmosphere, that knowledge came from the Galileo probe that actually descended into those crushing depths, transmitting data until the very moment it was destroyed by the conditions we imagined experiencing. When we spoke of the sulfuric acid clouds wrapping Venus, that understanding emerged from Soviet Venera probes that actually landed on that hellish surface, surviving just long enough to send back images of a world that exists at the limits of what planets can become. But our journey reveals something even more profound about the nature of exploration itself. We've discovered that the solar system isn't just a collection of 8 worlds orbiting the sun. It's an integrated system where everything influences everything else, where Jupiter's gravity shapes the asteroid belt, where Saturn's moons create features in its rings, where the solar wind strips atmospheres from unprotected worlds, while magnetic fields preserve them for billions of years. Mars teaches us about the fragility of planetary climates, showing us what happens when a world loses its magnetic field and watches its atmosphere leak away to space. Venus demonstrates the terrifying power of runaway greenhouse effects, a cautionary tale written in temperatures hot enough to melt lead. Earth reminds us that habitability requires an almost impossibly delicate balance of factors, from the right distance from the sun to the presence of a large moon that stabilizes our axial tilt. The gas giants reveal how matter behaves under conditions that push physics to its limits. Jupiter's metallic hydrogen oceans exist in a state that we can barely create in laboratories for microseconds, yet they persist for billions of years in the planet's interior, generating magnetic fields that extend millions of kilometers into space. Saturn's rings demonstrate how gravity can organize countless individual particles into structures of breathtaking beauty and mathematical precision. The ice giants show us worlds where water exists as supersonic ice, where methane falls as snow, where magnetic fields wobble through space in configurations that challenge our understanding of how planetary dynamos work. Each world operates according to the same physical laws, yet each has found its own unique expression of what it means to be a planet. Perhaps most remarkably, our journey reveals that we ourselves are products of this same cosmic system. The iron in our blood was forged in the cores of massive stars that exploded billions of years ago. The calcium in our bones came from stellar nucleosynthesis that scattered heavy elements throughout the galaxy. The oxygen we breathe was created by ancient bacteria that transformed Earth's atmosphere from carbon dioxide to the nitrogen-oxygen mixture that sustains complex life. We are literally made of stardust, temporary arrangements of matter that have somehow become aware of their own cosmic heritage. Tonight, as we've journeyed alien worlds, we've been eyed through these participating in the universe's process of self-discovery. Matter that was once scattered through interstellar space has organized itself into brains capable of contemplating the worlds where similar matter still resides. This perspective transforms how we understand our place in the cosmic order. We're not separate from the planets we've visited. We're part of the same story, products of the same processes that created Mercury's iron core and Jupiter's hydrogen atmosphere. The elements that make up our bodies have traveled through stellar cores, supernova explosions, and cosmic dust clouds before finding their way into the chemistry of life on Earth. The spacecraft we've sent to explore these worlds represent extensions of human consciousness, robotic ambassadors carrying our curiosity across distances that would take human travelers decades or centuries to cross. When Voyager photographed Neptune's Great Dark Spot, or when Cassini measured the thickness of Europa's ice shell, those instruments were functioning as our sensory organs, gathering information that our biological senses could never directly perceive. But technology has limitations that imagination doesn't. No spacecraft will ever descend through Jupiter's metallic hydrogen core or swim through Venus's sulfuric acid clouds. No human will ever walk on Mercury's sun-baked surface or breathe the thin air in Mars's ancient river valleys. The journey we've taken tonight exists only in the realm of thought and wonder, yet it's grounded in real knowledge gathered by real explorers who push the boundaries of what's possible. This is the power of scientific imagination, the ability to take measurements and data and transform them into visceral experiences that make distant worlds feel tangible and real. When we describe the sensation of sinking through layers of different atmospheric pressure, or the experience of encountering metallic hydrogen for the first time, we were translating scientific knowledge into emotional reality. Every number in a research paper represents something that actually happened, something that exists right now in the solar system around us. Jupiter's Great Red Spot is spinning at this very moment, a storm larger than Earth that has persisted since before the United States existed as a nation. Saturn's rings are orbiting the right planet now, billions of ice particles following mathematical laws with precision that would make a clockmaker weep with envy. Neptune's winds are howling through that distant blue atmosphere at speeds that exceed anything in our earthly experience. The planets don't care that we exist. They don't notice our spacecraft or our telescopes or our curiosity. They simply are, following the laws of physics, moving through their orbits, existing as they have for billions of years, and will continue to exist for billions more. But we care, we notice, we wonder, and that transforms everything. When consciousness encounters the universe, something new emerges that didn't exist before. The planets become more than just collections of matter following gravitational laws. They become worlds with personalities and stories, places that inspire wonder and fear and curiosity in equal measure. Mercury becomes the scarred warrior, bearing the wounds of cosmic bombardment with stoic endurance. Venus becomes the toxic beauty, gorgeous from a distance, but deadly up close. Mars becomes the melancholy dreamer, remembering better days when rivers flowed across its surface. These aren't just poetic metaphors. They're expressions of how consciousness interacts with reality, how awareness creates meaning from raw physical processes. The universe doesn't need us to observe it, but observation adds something precious that wouldn't exist otherwise. A moment of appreciation, a flash of understanding, a sense of connection between the tonight observer and the observed. You've been part of that process. By following this journey through impossible worlds, by letting your imagination soar through environments that would destroy any physical body, you've participated in the universe's ongoing conversation with itself. You've been consciousness exploring consciousness, matter contemplating matter, stardust wondering about the stars from which it came. The solar system will continue its ancient dance long after you've returned to sleep. The planets will keep spinning in their appointed orbits, following the same gravitational choreography they've performed for billions of years. But something has changed. Your awareness of these worlds has added a new dimension to their existence. They're no longer just distant lights in the sky. They're places you've visited, worlds whose secrets you've shared, environments you've experienced through the power of informed imagination. This is what makes the impossible journey possible. Not technology or spacecraft or magical powers, but the remarkable capacity of consciousness to transcend the limitations of physical existence through knowledge and wonder. We can't build machines that would survive the metallic hydrogen seas of Jupiter, but we can understand what such seas would be like, based on the physics of matter under extreme pressure. We can't breathe the sulfuric acid atmosphere of Venus, but we can comprehend the chemistry that creates such hostile conditions. Knowledge becomes a form of travel, understanding becomes a way of touching distant worlds, and imagination becomes the vehicle that carries consciousness across impossible distances. The journey we've completed tonight demonstrates that the human mind is perhaps the most remarkable phenomenon in the known universe, capable of reaching across billions of kilometers of space to commune with worlds that exist in conditions beyond direct experience. As you prepare for sleep, knowing that you've traveled farther than any human has ever gone, remember that this capacity for wonder is what makes us human. Other species navigate their environments with precision. Remarkable. They build complex structures, communicate sophisticated information, even use tools to manipulate their surroundings. But only humans, as far as we know, possess the ability to contemplate the cosmic context of their existence, to send explorers across the solar system, to imagine what it would feel like to touch the face of Jupiter or fall through the rings of Saturn. This gift of cosmic consciousness comes with responsibility. We're the only species on Earth capable of understanding the threats our planet faces, from climate change to asteroid impacts to the eventual death of our sun. We're also the only species capable of doing anything about those threats. The knowledge we gain from studying other planets isn't just intellectually satisfying, It's practically essential for understanding how planetary systems work, including our own. Venus teaches us about greenhouse effects run amok. Mars shows us what happens when a planet loses its magnetic field and atmosphere. The gas giants demonstrate how worlds can maintain dynamic systems over billions of years. Every planet we study adds to our understanding of how the universe works. Knowledge that could prove crucial for humanity's long-term survival and prosperity. The spacecraft we've sent to explore these worlds represent investments not just in scientific knowledge, but in human future. As we learn more about how planets form and evolve, we better understand what makes Earth special and how to protect the conditions that allow life to flourish. As we develop the technology needed to function in hostile environments like space, we create capabilities that could someday allow humanity to become a multi-planet species, ensuring our survival even if something catastrophic happens to Earth. But beyond practical considerations, the exploration of other worlds feeds something essential in the human spirit. We are explorers by nature, driven to see what lies beyond the next horizon. Our ancestors crossed oceans and climbed mountains and ventured into polar regions, not because they had to, but because they couldn't resist the call of the unknown. That same impulse drives us to send robots to Mars and plan missions to Europa and dream of someday walking on worlds that orbit other stars. The impossible journey we've taken tonight connects us to that ancient human tradition of exploration. We've pushed beyond the boundaries of direct experience to encounter worlds that challenge everything we thought we knew about what planets can be. We've touched conditions that exist at the very limits of what matter can become, witnessed phenomena that operate according to physics pushed to their extremes. In doing so, we've discovered that the solar system is far stranger and more wonderful than anyone imagined when humans first looked up at wandering stars and wondered what they might be. Each world tells its own story of cosmic evolution, of how matter and energy organize themselves under different conditions of temperature, pressure, and gravitational influence. The diversity is staggering, from Mercury's scorched craters to Neptune's supersonic winds, from Venus's crushing atmosphere to Jupiter's metallic hydrogen seas. Yet all of these worlds emerged from the same primordial cloud of gas and dust that gave birth to our Sun 4.5 billion years ago. They're all part of the same family, siblings in the cosmic sense, shaped by the same fundamental forces, yet expressing those forces in radically different ways. Tonight, you've become part of that family story. You visited every world in our solar system, experienced conditions that span thousands of degrees in temperature and millions of times in pressure, witnessed weather systems that dwarf anything on Earth and geological processes that operate on scales of cosmic time. You've done the impossible, gone where no human could ever go, touched the untouchable through the power of knowledge and imagination working together. Rest now in the knowledge that you carry within your consciousness direct experience of worlds beyond counting. The planets will be there tomorrow, continuing their eternal dance around the sun, but they'll be different for you now. No longer just points of light in the night sky, but places you've been, worlds whose secrets you've shared, environments that have become part of your expanded understanding of what it means to exist in this remarkable universe. The cosmos is vast and ancient, and filled with wonders beyond imagination, but tonight you've made it a little smaller, a little more familiar, a little more like home. Sweet dreams, cosmic traveler. May your rest be as peaceful as the silence between worlds, as deep as the gravitational wells we have explored, and as infinite as the space all things that connects in the grand symphony of existence. The morning will find you changed in ways you might not immediately recognize. When you next look up at the evening sky and see those wandering stars that have captivated humanity since we first developed eyes to see them, you'll carry with you the memory touché of having each one. That pale dot moving slowly against the background of fixed stars isn't just Jupiter anymore. It's a world you've fallen through, a place where metallic hydrogen flows in oceans larger than continents, where storms rage with the fury of entire planetary atmospheres. But our impossible voyage has revealed something even more profound about the nature of existence itself. We've discovered that the universe operates according to principles of incredible complexity and breathtaking simplicity working in harmony. The same gravitational laws that keep your feet planted on Earth's surface also sculpt the rings of Saturn into mathematical perfection. The same nuclear processes that power our sun also forged the iron in your blood billions of years ago in the cores of ancient stars. This interconnectedness extends beyond mere physical processes into the realm of consciousness itself. When you contemplated the crushing pressures in Jupiter's depths or imagined floating through Saturn's ring system, you were participating in something remarkable. Matter that was once scattered throughout the cosmos has organized itself into a configuration capable of understanding its own cosmic heritage. You are the universe examining itself, temporary arrangements of stardust that have somehow developed the ability to wonder about the stars from which they came. Consider the profound implications of this realization. Every atom in your body has a story that spans billions of years and countless cosmic environments. The hydrogen that makes up most of your water molecules was forged in the first moments after the Big Bang, making it literally the oldest matter in existence. The carbon that forms the backbone of your DNA was created in stellar cores through nuclear fusion processes identical to those still powering our sun. The oxygen you breathe with every breath came from massive stars that ended their lives in supernova explosions so violent they outshone entire galaxies. These elements didn't simply appear in your body by chance. They traveled through interstellar space for eons, became part of the molecular cloud that collapsed to form our solar system, were incorporated into the early Earth through countless impacts and geological processes, and eventually found their way into the complex chemistry that creates and sustains life. You are literally made of the same materials that compose the worlds we visited tonight, arranged differently, but sharing the same fundamental cosmic ancestry. This perspective transforms our understanding of what it means to be human. We're not separate observers looking out at a foreign universe from our isolated planetary home. We're integral participants in cosmic evolution, conscious expressions of the universe's ongoing process of self-organization and self-discovery. The curiosity that drove you to follow this journey through impossible worlds is the cosmos itself seeking to understand its own nature through the temporary vehicle of human consciousness. The spacecraft we've sent to explore these planetary environments represent extensions of this cosmic self-awareness. When Voyager photographed the Great Red Spot, or when Cassini measured the composition of Titan's atmosphere, those instruments were functioning as the universe's own sensory organs, gathering information about cosmic processes that would otherwise remain hidden from direct observation. Every measurement they transmitted back to Earth added to the universe's growing understanding of its own complexity and beauty. But technology, no matter how sophisticated, can only take us so far. The robotic explorers that have visited every planet in our solar system operate according to predetermined programming, capable of following instructions and gathering data, but lacking the spark of genuine wonder that transforms raw information into meaningful experience. They can measure temperatures and pressures and chemical compositions with exquisite precision, but they cannot feel awe at the sight of Saturn's rings or experience the humbling vastness of Jupiter's great red spot. That capacity for wonder, for emotional response to cosmic beauty, remains uniquely biological. It emerged through billions of years of evolution on a single small planet. Yet it allows us to reach across impossible distances, to commune with worlds that exist in conditions beyond direct experience. The journey perhaps we've taken tonight demonstrates that consciousness is the most remarkable phenomenon in the known universe, capable of transcending physical limitations through the power of informed imagination. This transcendence isn't just poetic metaphor, it's a genuine form of exploration that yields real understanding about the nature of cosmic environments. When we described what it might feel like to sink through layers of increasing atmospheric pressure on Venus, we were translating scientific measurements into experiential knowledge. The data gathered by Soviet Venera probes provides objective information about temperature and pressure gradients, but human consciousness transforms that information into something approaching direct experience. This transformation reveals something profound about the relationship between objective and subjective reality. The universe exists independently of our observation, following physical laws that operated for billions of years before consciousness emerged and will continue operating long after all biological awareness has ceased. Yet consciousness adds something precious that wouldn't exist otherwise: the capacity to appreciate beauty, to find meaning in patterns' wonder, to experience at the sheer improbability of existence itself. When you contemplated the hexagonal storm at Saturn's North Pole, or imagined swimming through metallic hydrogen in Jupiter's interior, you are creating experiences that exist nowhere else in the universe. No other conscious beings we know of have that ever had thoughts quite like yours, felt wonder at quite the same cosmic phenomena, or participated in quite the same journey of discovery. Your individual consciousness represents a unique perspective on cosmic reality, a one-time only experiment in how matter can organize itself to contemplate its own existence. Yet paradoxically, this uniquely personal experience connects you to something universal. Every human who has ever looked up at the night sky and wondered about the nature of those distant lights has participated in the same fundamental process of cosmic self-reflection. From ancient astronomers who first mapped the movements of planets, to modern scientists who send robotic explorers across billions of kilometers of space, we're all part of the universe's ongoing effort to understand itself. The knowledge we've accumulated about planetary environments represents a collective achievement spanning centuries of human curiosity and ingenuity. Galileo's first optic telescope observations of Jupiter's moons laid the groundwork for understanding that other worlds could have their own satellite systems. Kepler's mathematical analysis of planetary motions revealed the underlying gravitational architecture that governs orbital mechanics. Newton's laws of motion and gravitation provided the theoretical framework needed to navigate spacecraft across interplanetary distances. Each has generation built upon the discoveries of previous generations, adding new observations, refining theoretical models, and developing more sophisticated tools for cosmic exploration. The journey we've taken tonight represents the culmination of this centuries-long process of discovery, transforming distant points of light into detailed worlds with known temperatures, pressures, atmospheric compositions, and geological histories. But our understanding remains incomplete, and perhaps always will be. Every answer we discover seems to raise new questions that we hadn't thought like hydrogen in Jupiter's interior to ask. The metal behaves according to physics we can barely model with our most advanced computers. The superionic ice in Uranus and Neptune exists in states that challenge our basic understanding of how matter can behave under extreme conditions. The atmospheric dynamics that drive Neptune's supersonic winds operate through mechanisms we're still struggling to comprehend. These remaining mysteries aren't failures of scientific inquiry. They're invitations to deeper understanding, puzzles that will motivate future generations of explorers and researchers. The universe seems designed to reward curiosity with endless discoveries, each one revealing new layers of complexity and beauty that we hadn't previously imagined. There will always be more to explore, more to understand, more to wonder about. This inexhaustible mystery is perhaps the universe's greatest gift to consciousness. In a cosmos where every question had definitive answers, where every phenomenon was completely understood, there would be nothing left to discover, nothing left to explore. Instead, we find ourselves in a reality that seems perfectly calibrated to sustain wonder indefinitely, where each new discovery opens doorways to realms we hadn't known existed. The journey through planetary interiors we've completed tonight represents just one thread in this vast tapestry of cosmic mystery. Beyond our solar system lie billions of other planetary systems orbiting distant stars, each one potentially harboring worlds that would make our local planet seem ordinary by comparison. Hot Jupiters orbiting so close to their stars that their atmospheres are heated to stellar temperatures. Super-Earths with masses several times greater than our homeworld, possibly harboring forms of geology and atmospheric dynamics we can barely imagine. Rogue planets wandering through interstellar space without any star to warm them, their surfaces frozen, but their interiors possibly harboring subsurface oceans warmed by radioactive decay. The diversity of exoplanets discovered in recent decades suggests that planetary formation can produce worlds far stranger than anything in our own solar system. There might be carbon planets where diamonds form deep underground, ocean worlds covered entirely by liquid water hundreds of kilometers deep, or planets with atmospheres of vaporized rock and metallic clouds that rain liquid metal. Each of these environments would offer its own impossible journey, its own unique demonstration of how matter and energy can organize themselves under different cosmic conditions. Yet tonight we've focused on the 8 worlds that share our sun, the planets that formed from the same primordial cloud of gas and dust that gave birth to Earth. These are our cosmic siblings, shaped by the same fundamental processes, but expressing those processes in radically different ways. Understanding them helps us understand not only how systems form planetary evolve, but also what makes our own world special and how we might protect the delicate conditions that allow life to flourish. The atmospheric dynamics we've witnessed on Venus provide cautionary lessons about greenhouse effects and climate stability. The geological history revealed fields protected by Mars demonstrates how planetary magnetic atmospheres from being stripped away by stellar radiation. The complex weather systems of the gas giants show us how rotation and internal heat can drive atmospheric circulation on scales that dwarf terrestrial weather patterns. Every planet we've visited tonight operates as a natural laboratory, demonstrating physics under conditions we could never replicate on Earth. From the surface chemistry of Mercury to the exotic matter phases in Neptune's interior, each world pushes the boundaries of what we thought possible and challenges us to expand our understanding of how the universe works. This knowledge isn't just academically interesting, it's practically essential for understanding our own planet's place in cosmic evolution and for developing the technologies that might someday allow humanity to become a spacefaring civilization. Learning how atmospheres form and evolve helps us understand climate change on Earth. Studying magnetic field generation in planetary cores informs our understanding of how Earth's protective magnetosphere operates. Analyzing the geological processes' insights into the forces that shape planetary surfaces provides that continue to reshape our own impossible world. The journey we've taken tonight also serves another crucial purpose. It expands our conception of what's possible. By imagining ourselves descending through environments that would instantly destroy any physical body, we push beyond the limitations of direct experience to explore realms that exist only in the intersection of knowledge and imagination. This capacity for transcendent exploration is uniquely human, a gift that allows us to commune realities far with cosmic beyond our immediate sense. As you prepare Tauri range, drift towards sleep, carrying with you the memories of worlds beyond counting. Remember that this capacity for wonder is what distinguishes consciousness from mere information processing. Machines can gather data about planetary temperatures and atmospheric compositions with perfect accuracy, but only beings can transform that data into experiences of beauty and meaning. Only awareness can look at measurements of metallic hydrogen and feel awe at the exotic states matter can achieve under extreme conditions. Tonight, you've participated in the universe's ongoing process of self-discovery, using the remarkable gift of human consciousness to explore cosmic environments that exist at the very limits of what's physically possible. You've touched conditions that challenge our understanding of matter and energy, witnessed phenomena that operate according to physics pushed to their extremes, and experienced the profound interconnectedness that links all cosmic processes across scales from atomic to planetary. The planets will continue their eternal dance around our sun, following gravitational laws with mathematical precision. But they'll be different for you now. No longer just distant lights moving against the stellar background, but worlds you've visited, places whose secrets you've shared, environments that have become part of your expanded understanding of cosmic reality. Sweet dreams, fellow traveler in this magnificent universe. May your rest be filled with the peace that comes from having touched infinity, and may you awaken tomorrow with eyes better able to see the wonder that surrounds us always, in every atom, in every breath, in every moment of consciousness contemplating its own cosmic heritage. The impossible journey ends where it began, in the quiet space of human awareness, but you carry within you now the memory of having been everywhere at once, touching the face of worlds beyond imagination through the miraculous gift of informed wonder. The journey back from Neptune carries us through a solar system forever changed by our impossible passage. We've witnessed matter pushed to its absolute limits, touch conditions that exist nowhere else in creation, and experience the profound interconnectedness that binds all cosmic processes together across unimaginable scales of space and time. But there's something else our voyage has revealed, something that goes beyond measurements of temperature and pressure and atmospheric composition. We've discovered that the act of exploration itself transforms both the explorer and the explored. The planets remain the same collections of matter following gravitational laws they've obeyed for billions of years. Yet they've become something more through our conscious engagement with their mysteries. When you imagined sinking through Jupiter's metallic hydrogen oceans, or floating through Saturn's delicate rings, you weren't just processing scientific information. You were creating experiences that exist nowhere else in the universe. Moments of consciousness encountering cosmic reality in ways that no other known form of awareness has ever achieved. These experiences become part of you, expanding your understanding of what existence can encompass and what it means to be conscious in a universe of infinite possibility. This transformation works both ways. The planets don't need our observation to continue their ancient orbital dance, but our awareness adds something precious that wouldn't exist otherwise. A moment of appreciation for Saturn's rings becomes part of the universe's growing capacity for self-reflection. A flash of wonder at Jupiter's Great Red Spot contributes to the cosmos becoming more conscious of its own beauty and complexity. Every made measurement by our robotic explorers, every image transmitted across billions of kilometers of empty space, every scientific discovery that reveals new aspects of planetary environments becomes part of humanity's expanding relationship with the cosmic neighborhood we inhabit. We're not just accumulating data about distant worlds. We're developing genuine relationships with places we may never physically visit, but can know intimately through the marriage of scientific observation and informed imagination. Consider what this means for our understanding of exploration itself. The age of human exploration on Earth involved brave individuals venturing into unknown territories, mapping coastlines and mountain ranges and polar regions through direct physical presence. But the exploration of other worlds requires a different kind of courage. The willingness to extend consciousness across impossible distances and imagine ourselves into environments that would destroy any biological form instantly. This new form of exploration doesn't diminish the achievement of those who crossed oceans in wooden ships or climbed unconquered peaks with primitive equipment. Instead, it represents evolution in human capability, the development of tools and techniques that allow consciousness to transcend the limitations of physical embodiment. When Voyager transmitted images of Neptune's Great Dark Spot, or when Cassini measured the thickness of Europa's ice shell, those robotic explorers were functioning as extensions of human awareness, carrying our curiosity across distances that would require lifetimes of travel at any achievable velocity. Yet the robotic explorers have their own limitations. They can measure and analyze and transmit data with exquisite precision, but they cannot experience wonder at the beauty of what they observe or feel the profound humility that comes from contemplating cosmic scales that dwarf all earthly experience. That capacity for emotional response to cosmic phenomena remains uniquely biological, the product of billions of years of evolution that somehow produced matter capable of appreciating its own cosmic journey heritage. The we've shared tonight demonstrates that this for wonder isn't just a pleasant capacity side effect of having evolved consciousness. It's a fundamental tool for understanding reality itself. Scientific measurements provide objective information about planetary conditions, but human consciousness transforms that information into knowledge that feels lived in and experiential. When we describe the sensation of pressure building around us as numbers we descended through Venus's atmosphere, we were translating abstract into something approaching direct experience. This translation process reveals something remarkable about the nature of knowledge itself. All learning involves connecting new information to existing patterns of understanding, but cosmic exploration requires us to stretch those patterns beyond anything our evolutionary heritage prepared us for. Our brains evolved to navigate terrestrial environments where temperatures vary by perhaps 50 degrees Celsius and pressures change by at most a few percent. Yet somehow we can comprehend worlds where temperatures span thousands of degrees and pressures vary by factors of millions. This cognitive flexibility represents one of consciousness's most extraordinary achievements. We can take measurements that exist as puractions and abstract transformal, understanding them into this of how matter behaves under conditions that exist nowhere in our direct experience. The metallic hydrogen in Jupiter's interior becomes not just a theoretical state of matter described by physics equations, but something we can almost feel flowing around us like an impossible ocean of liquid metal. The fact that we can perform this cognitive transformation suggests that consciousness possesses capabilities we're only beginning to understand. The same neural networks that evolved to help our ancestors track animals across African savannas can somehow comprehend the atmospheric dynamics of gas giants orbiting other stars. The pattern recognition systems that develop to identify edible plants and avoid predators can process information about planetary formation processes that occurred billions of years before Earth existed. This remarkable cognitive flexibility hints at deeper connections between consciousness and cosmic processes. Perhaps the ability to understand the universe emerges naturally from the same organizational principles that created the universe in the first place. The patterns that consciousness recognizes in cosmic phenomena might reflect genuine structural relationships that exist at the deepest levels of reality. When you contemplated the hexagonal storm at Saturn's North Pole, or imagine the crystalline structure of superionic ice in Neptune's interior, you were engaging with mathematical relationships that govern how matter organizes itself under extreme conditions. These relationships exist independently of human observation, but consciousness provides the means through which the universe can appreciate its own mathematical elegance and structural beauty. This perspective transforms our understanding of what it means to be conscious beings in a cosmic context. We're not accidental observers who happen to find ourselves in a universe filled with interesting phenomena to study. We're integral participants in the universe's ongoing process of self-organization and self-understanding. The curiosity that drives scientific exploration represents the cosmos itself, seeking to comprehend its own nature through the temporary vehicle of biological awareness. The spacecraft we've sent to explore planetary environments serve as extensions of this cosmic self-reflection. When these robotic explorers analyze the chemical composition of Martian rocks or measure the magnetic field strength gathering in Jupiter's magnetosphere, they're information that contributes to the universe's growing understanding of its own complexity and history. Every data point transmitted back to Earth becomes part of the expanding library of cosmic knowledge that consciousness has been building for centuries. But this knowledge accumulation isn't just an abstract intellectual exercise. It's a deeply practical endeavor that influences how we understand our own place in cosmic evolution and how we might navigate the challenges that face any technological civilization. The atmospheric dynamics we observe on Venus provide crucial insights into greenhouse effects and climate stability. The geological history revealed by Mars demonstrates how planetary magnetic fields protect atmospheres from being stripped away by stellar radiation. Every world we study adds to our understanding of the conditions necessary for habitability and the factors that determine whether planets can maintain those conditions over geological timescales. This knowledge becomes essential as we contemplate humanity's long-term future and the possibility of becoming a multi-planet species capable of surviving, even if something catastrophic happens to Earth. Tonight we've accomplished something that exists at the very intersection of knowledge and wonder, touching worlds that would annihilate any physical form, yet feeling them become real through the miraculous marriage of scientific understanding and human imagination. From Mercury's scorched silence to Neptune's howling winds, we've witnessed the extraordinary diversity that emerges when matter and energy dance together under different cosmic conditions. Sweet dreams, fellow explorer. Tomorrow, when you glimpse those wandering points of light in the evening sky, you'll carry with you the profound memory of having been everywhere at once in our magnificent solar system. Being everywhere at once in our magnificent solar system.